Okay, let us continue our lecture. So in the previous lecture we stopped at the point where we considered the integral representation of the solution of the Dirichlet boundary problem for Laplace equation in the disk and in the ball. And now we continue this. And I remind you that the Poisson kernel for the ball has a form where the angle gamma is the angle between the two vectors R and R0, where R runs along a sphere, the boundary of the ball, and R0 is some fixed point where we need to find our solution, the value of our solution. So now we need to find the explicit expression for this cosine or the angle gain. To this end, we can write the following standard representation of the point x0 in the spherical coordinates. Then the unit vectors, the corresponding unit vectors are as follows. And for x0, it has the form and so we can find the cosine of the angle gamma. My standard formula. It can be written after some algebra such a form. Okay, so all the ingredients of this formula are explicitly defined, and we can use it. We can substitute it in the integral that was written in the previous lecture. Notice that Poisson kernel is an infinitely differentiable function. Belongs to C infinity with respect to variables for the ball and R0, phi0 disk. And this fact is easily seen from these explicit expressions, and it follows from the observation that for any integral point of the ball or the disk, this function does not vanish. not 0. And when any other points, this is an infinitely differentiable function. So, this implies the following corollary. Which says that any harmonic function in 3 or 2-dimensional space possess the derivatives of arbitrary order. The proof. Consider some point R0, x0 belonging to the domain omega. Omega is a domain of harmonicity. That is the function u satisfy the Laplace equation. This is the main. Let us construct some ball. Bounded by the sphere gamma. And of some radius, with radius r, and this ball completely belongs to the domain of harmonicity. And x0 belongs to this ball. Let me draw a picture. This R3. Here is some domain of harmonicity. Here is point x0, and here is a sphere gamma, and the sphere bounds the ball, and the point x0 belongs to this ball. Then the function u restricted to the boundary gamma, we denote it as f of x, and it is a known function because we know this function u, harmonic function. And we can apply the Poisson integral in order to evaluate this function u at the point x0. The formula was written in the previous lecture, and I do not write it here. And as is seen from this formula, this integral is uniformly convergent with respect to, or when R0, theta 0, phi 0 runs along the sphere, belongs to the ball, and this fact follows from the observation that this integral is over a bounded domain, over gamma, which is a bounded set, and the integrand of this integral is a continuous function. So this integral can be differentiated with respect to these parameters arbitrary number of times, and this proves the fact that harmonic function is an infinitely differentiable function. So I should stress, the proof is finished, so I should stress that initially, when we solve this equation, we only imply that this function is only twice differentiable. That is, this expression should be defined. But then we show that if the function u satisfies this equation, then it is infinitely differentiable, in fact. And, okay. The next paragraph. Solution of boundary problems for the Laplace and Poisson equations by means of the Fourier method. So the Fourier method. Another name for this method is a method of separation of variables. It is a powerful method for solution of linear equations, special derivatives, when these equations possess some symmetries, and the domain where the solution is solved complies with these symmetries. I consider this general method on a simple example, but the main steps, but it will be clear how to apply it in a general setting, and I just show you the main steps how it can be done. Okay. Let us consider the solution of the two-dimensional Laplace equation. In the domain D, which is a rectangle. Picture. Point A, point B, and this is domain D. We see that, notice that the Laplace equation, or the Laplace operator, is invariant with respect to translations of such a form. And the integral lines of this symmetry transform looks as follows. It's clear that they are some rectilinear curves. We have some point, initial point, and then we apply this symmetry transform to some line. This line, another one, but it is rectilinear. And we see that the boundary of this domain consists of the lines of the symmetry transform. That is, they are rectilinear. So we may hope that the method of separation of variables give us the result, give us the solution of this problem, of the problem and of the boundary problem. In fact, it is not formulated here and will be given below. So we have such an equation in this domain And we have the following boundary conditions. These are all the boundaries of these boundaries. And this one, another. So we have the Dirichlet problem of the Laplace equation on a plane, or in fact in a rectangle. Then we seek the solution in the form. Where V in W satisfies the following boundary problems. This is for V, and that's for W. Then we see that due to linearity of the equation and the boundary conditions, the sum of V and W does satisfy this initial equation. That is, if we add V and W, then this sum satisfies the Laplace equation due to the fact that V and W satisfies this equation. And their sum, the sum of these two functions, satisfies these boundary conditions due to the fact that the function V and W satisfies this one. It is easy to see. Then we consider. Then we need to find the solution of these two Dirichlet problems. And we begin with this one, and in fact we solve only this problem because the solution of this problem is analogous to the problem for the function V. And we begin with seek the solution of this boundary. Okay. Excuse me, could you close the door? Okay, let us seek for the solution of this system of equations in the form. That is, we seek the solution in the form of a product of two functions which depends separately on the variable x, independent variables x and y. This is the main point of the method of separation of variables. Okay, of course, one can wonder whether one meets some solutions or not when one seeks the solution in such a form. We will show below in our future lectures that in fact such particular, of course it is a particular solution, but we will show our future lectures that the general solution of the problem is a linear combination of such a particular solutions. So, when we find all such particular solutions, we can find easily the general solution of the initial problem. And we will prove this statement in our future lectures. But now we just use this statement. And so we substitute this representation of the function v into the equation and into the boundary conditions. And find the following. Okay, and so we have just differentiate, and then we need to, so to say, to separate variables. That is combined this expression in such a form when it contains the sum of the functions, and these functions depends solely on one independent variable. Namely, we just multiply this expression by 1 over x and y and find. This is the sum of two functions which depends on independent variables. In virtue of the fact that the variables x and y are independent, this equality holds only if and only if when this function and this function are constants. This follows from the fact that x and y are independent variables. And in fact, this constant must be equal to each other with the opposite sign. The modulus of these two constants are equal and they possess an opposite sign. So we have such constant, this is minus 1. Then we satisfy this equality. Let us turn to this equality. We denote this ratio as minus lambda squared. This is some constant. And this ratio we have to denote as lambda squared. Then their sum is 0. So we have two ordinary differential equations. One. Then we have to substitute this representation into the boundary condition. Then we have the boundary conditions for x of x. We know that the function v, the boundaries x is equal to 0 and boundaries x is equal to a, must vanish. Then we have the formal relation. And as long as we seek for non-trivial solution, which is not 0, then we can just cancel out these functions y. And then we have the function x is equal to 0 at the points a and 0. As for the boundary condition for the function y, we'll consider it below, but now we can solve the first equation with the corresponding boundary condition. Yeah? And boundary conditions. And the general solution of this equation is readily found, which is just an equation for harmonic oscillator. So, A as for A, we have such a general solution, which is a linear combination of sine and cosine. Then we impose the boundary conditions. And we have first boundary condition, that is the function x vanishes at the point 0, implies that this is 0 and this combination must be 0. Then we have b is 0. Then we substitute, we use this implication and substitute the second boundary condition at the point A into the rest of this expression. And obtain the following equation. So, since we seek for a non-trivial solution, A is not 0. A large is not 0, A small also. A is not 0, but lambda, the constant lambda, must be of the form. In fact, we solve the equation sine of lambda times A is equal to 0. That's the equation on lambda, and we find that lambda has such a form. Here, n is equal to 0 is excluded, because when n is equal to 0, lambda is equal to 0, and the whole expression, the rest expression, this is absent, and the whole expression is 0. That's we have a trivial solution. When n is negative, we can just factor out the sign, and we obtain the same solution as for the positive n. So, if you consider only independent solutions, then we must suppose that n runs from 1 to infinity. All integer numbers from 1 to all natural numbers, of course, in fact. And then we have such a solution of the equation A. They are enumerated by the index n, which runs from 1 to infinity. They have such a form. Now we turn to the solution of the equation B. Yeah. The general solution of such an equation is follows. It is a linear combination of exponents, and here we use the fact that lambda is equal to lambda n, as we found from the solution of the equation A. Then the product of the solutions, which is V sub n, sometimes yn, can be written in the form here we redefine the arbitrary constants an and bn, and just and an, for example, is equal to, excuse me, let me denote these constants as a small and small. A small n much a n times a n with tilde. A and b and small are just arbitrary constants, and we have to find them from the another boundary condition, which was given to us. Okay. Then the general solution is a linear combination of these particular solutions. This function satisfies the Laplace equation. And the boundary conditions we have already used. This one. But we have another pair of boundary conditions, and then we impose them other boundary conditions. When we impose these boundary conditions on this function, we have in fact, we just substitute here the point y is equal to 0, and here we have the point y is equal to b into this expression, and we have such inequalities, and the function b is equal to mu sub 1, and at the points where y is equal to 0, and it is equal to mu sub 2, and the points where y is equal to b. And we have to find the unknown coefficients a(n) and b(n) from these two equations. In fact, the left-hand side of these equations is a Fourier series, and in order to find these coefficients, we have to expand the right-hand side in the Fourier series. Or we just need to use the following integral. Remind that call that there is such a relation. That these two is equal to delta n k, that these two functions are orthonormal with respect to such a scalar product. And or just we can evaluate these integrals by the standard means and convince yourself that this is indeed the case. Then we multiply these integrals by the corresponding sine functions and integrate over the interval from 0 to a such a form, and even multiply it by the form factor. Okay, and then we use this expression and we multiply this series and integrate this series term by term. Okay. And integrate the series term by term, we find that okay, let's stop at this point. Okay, let us continue. If we multiply these two equations by the sine function and integrate over the interval from 0 to a, we find, or we come to the following system of linear equations. This is a system of linear equations, in fact of two linear equations for two unknowns, ak and bk. These functions are known, mu1 and mu2, and so these integrals are optional. In some cases they can be evaluated in closed analytical form, but in general these integrals have to be evaluated numerically, but in fact they are known. And then we can solve this simple system of equations and find ak and bk. Once we have there is a hyperbolic sign. And bk as a form. A small and B small, because I changed notation. Then the solution of our initial problem for the function v has the form as a bar, is written here, where the coefficients of the, in fact, the Fourier series, the coefficients of the coefficients a, k, and b, k are known. They are known numbers, and you can evaluate these integrals, find them. Then we completely specify the solution of the first problem for the function v, and as for the function w, the boundary problem can be solved analogously, and I leave this problem as an exercise for you, and we will consider it in the lecture. Okay, this section is finished, and the next section, we consider the application of the some simple example of application of conformal transformation in order to find the theory of complex variables in order to find the solutions of elliptic differential equation with partial derivatives, and for the problems formulated on the plane. Okay, namely, we consider flat parallel flow around cylinder and a plane of incompressible ideal fluid. So we start with the following derivation. Namely, we consider incompressible that is without viscosity, stationary, floor in two-dimensional space. That's on the plane. The system of equations for such a flow is characterized by some vector field of velocity. And in our case, consider planar problem, that the fluid flows along the plane, and due to the fact that it is incompressible, you can write the following condition. This equation reflects the fact that the fluid is incompressible. And due to the stationarity of the problem, the rotor of the vector field V is equal to 0. So we have such a system of equations. And we just have to solve this system of equations with a certain boundary condition. But in order to solve it, we introduce some useful concepts, namely the concepts of notion of potentials. And we start, in fact, we solve this equation in a general form by introducing the potential. Let's introduce potentials. We start with this equation. The form. We suppose the summation of repeated indices, namely it is a sum. Just shorthand notation for such a sum. Then introduce the set of functions u, which are related to the functions v in the form of a, where epsilon ij is a totally antisymmetric tensor. Its components 0, 1, and minus 1. In fact, is such a matrix. Then we can rewrite, we can express y in terms of u. It is easy to see that they are related in the simple form, and substitute into this equation. Then we have zero, and this can be written. Here is a double sum, remind you, yeah? Because there are two equal indices in this expression. And we can write it in the following form. You can write it more explicitly, just evaluating these two sums. Here's the following expression. As you know from the course of mathematical analysis, if one has the following equations, then one can write the general solution of this equation. And the general locally in some neighborhood of the given point. Small but finite neighborhood. And the general solution is written in the form that is the function u is a gradient of some scalar function psi. And where psi is called as a potential. fact, in our problems, there will be two potentials. This is one potential, and the another one will appear again. So it's potential, and we can express the function v in terms of this potential using this relation. And we have now I'll give you a geometric representation of this potential. Notice that the following relation holds. If you consider such a scalar product, the vector field v and the gradient psi, so we can write it. Then we substitute this expression for v, and arrive at the following expression. This tensor is symmetric with respect to the indices I and j, whereas this tensor is antisymmetric. And so this contraction, this double sum with respect to indices I and j, is equal to 0. One can easily check it by a little calculation or from this property. And so thus we see that the action of the vector field on the function psi is equal to 0, and it just means that if one introduces the so-called streamlines, which are the solutions of the following system of equations. It is a system of partial differential or of ordinary differential equations and can be solved. And let me draw a picture here. If we solve the system of equation and draw the integral lines, then these lines are what is called the streamlines. So to plane, consider the vector field v that we have at every point of the planes. The vector v depends on x and y. At every point we have such a vector. When we integrate the system of equations, we obtain some lines such that the vector v is tangent to this line at every point of this line, called streamline. And this equality implies that the streamlines are in fact can be found as a solution of the following equation, or are defined by this equation in terms of the potential. that is, the potential psi is constant along a streamline. And, of course, these constants are different for different streamlines, but along the streamline, as you see, yeah, because we can write this equation, the right-hand side of this equation, using this equality sets. This shows that streamlines are indeed, that psi is constant along streamlines. This is a physical interpretation of the potential psi. Now we turn to the second equation. Consider this equation. Then, as you know from general physics, first of all, we can apply the consideration as a bar. We can write the vector field V as a gradient of some function phi. Phi is another one potential. Then, combining these two representations, this one and this one, and this, we derive the following equations. In fact, this is a starting point. This is a starting point for reformulation of our problem in terms of the function in terms of analytical function of complex variables, because these two relations resembles the Cauchy-Riemann relations, and in fact, this is the case. And so, let us introduce the function W, which is a function of a complex variable z, which is equal to x plus iy. And then these two equations are the Cauchy-Riemann conditions for this function W. That means that this function W is analytical in some small neighborhood of the point Z. Therefore, W of Z is a locally analytical function. Okay, let us give the physical interpretation of this function. Consider the derivative of this function. This derivative can be written in such a form, as you know from the course of analytical functions. And using these relations, we can write this derivative in terms of v, and thus you see that this is just complex conjugate of complex function v large, where v is such a complex function. And from the physical reasons, it is clear that the function v and v star, that is the complex conjugate of v, are single-valued functions. And so the derivative of w with respect to z is also a single-valued function. Because we know at every point of the plane x and y, we know one value, single value of the velocity components, and we know this. We can restore the value of this function uniquely if we know the components of the velocity vector field. Another one observation. Observe that let's consider the following integral along a closed contour C, and then we can write it in such standard form, which of course you know. We reduce this integral to two integrals of free variables with respect to real variables, and write it such a form. Now, we give the physical interpretation to these two terms in terms of physical hydrodynamic interpretation of these two terms. As for the first term, or real part, this expression, we know that the vector tau with components dx and dy is tangent to the curve C. And so the first integral is a circulation of the vector v along the contour C. Circulation of the vector field v along the contour C, and it is clear from these expressions that such a vector is a normal to C. Because it is orthogonal to the tangent vector tau, as you can check by taking the scalar product of these two vectors, and vector 0. Then it follows from this observation that the second integral is a flux of the vector field field V through the circle or through the contour C. Okay. Then the next paragraph is called flat parallel flow around a cylinder. Now we consider the solution of the complex problem. Namely, we wish to find the velocity field of the fluid which flow around some impenetrable cylinder of an infinite length, and so the problem is in fact a planar. Let me draw a picture. Flat parallel. Around a cylinder. Picture. Is in fact complex plane Z. X and Y. There is a cylinder. And, the radius A, and the center of the circle is at the origin of the system of coordinates. It's A. So we have such a flow, incompressible ideal fluid, which flows around this cylinder. These are the streamlines, which we discussed above. And we have to solve the following system of equations. With the boundary conditions. These boundary conditions say that the cylinder is impenetrable. It is the projection of the velocity v to the direction x, x, vector x, and we have some velocity field like this. And the projection of this velocity field, let me draw it in the wrong way, in such form, then the projection be parallel must be zero, because, or in the other direction, because the cylinder is impenetrable. So, if we substitute these explicit expressions for V in terms of the potential, we will find that this implies that such derivative must be zero. And another one condition. This is boundary condition on the boundary of the domain where we solve our problem, but another, because this is an external problem, we have to impose the boundary conditions at infinity. So at infinity, we assume that we have some constant form of a fluid with such a components. We can write them in the form, produce 0 without vector sign. This is the modulus of this vector. And to introduce the angle alpha. In fact, it is the definition of the vector alpha of the angle alpha. This is boundary condition at infinity. That is, at infinity, at large distances from the origin of the system of coordinates, or from this cylinder, the fluid flows along straight lines, and at the angle alpha to the axis x, along such straight lines. Okay. Then we can rewrite this boundary condition in more useful form. Let me continue here. Such a projection is written in terms of phi as the derivative of phi with respect to r. We used already this fact. And so, at infinity, this derivative is equal to such a function where x over r is a unit vector. It has the components cosine phi and sine phi, and in fact it is a definition of phi. That is phi is an argument of z. So, as we know from the theorems or from the course of function of complex variables, in order to find, we know that the functions phi and psi are harmonic functions. In the domain, in our case, out of the circle. of x is equal to a. So we have to solve the Laplace equation, two Laplace equations, and in this domain with the given boundary conditions. But as we also know from the course which we delivered the previous semester, we know that this problem can be reformulated in terms of functions, of analytical functions. Then the function w of z, such function, which is a single valued function, is analytical in this domain. And in fact, we saw that this function is indeed analytical in this domain because in this domain, w, the real and imaginary components of w satisfy the Cauchy-Riemann conditions. And so its derivative is also an analytical function, but and moreover, this function is single valued. And we know that if the function is analytical outside of some circle and of course single valued, then it can be represented in terms of Lorentz series. So we doesn't need to solve the Laplace equations. We just can use the main facts from the theory of analytical functions. Thus, we have an equation and we know that the function which is analytical in the domain in some annual neighborhood can be represented in terms of Lorentz series. In our case, this annual neighborhood is centered at the origin of the system of coordinates. Therefore, the Lorentz series looks as follows, where alpha n are some complex constant, and in fact, we need to find these complex constants by using the boundary conditions which were given to us. So this is a general, in fact, this is a general solution of the Laplace equations for phi and psi. We already write it here without any procedure to solve. And then we need to use the boundary conditions to specify the complex coefficients alpha n. Okay, let me stop at this point and we will continue on the next lecture with the solution of this equation.